Let's talk about Unit 9, dimensioning. Dimensioning shows us the magnitude of the size of features. The previous chapters, we talked about different views and sections, auxiliary views, all sorts of ways to show the shape of things. Now we'll talk about how to attach values to those shapes. Dimensioning indicates the size of features and the location of features in reference to other features. What we'll talk about in the next unit is tolerancing. Tolerancing indicates the allowed variation in any given feature. The source for the rules for all of this is ASME Y14-5, dimensioning and tolerancing. You'll typically hear dimensioning and tolerancing grouped together because you usually do them at the same time. Some practices in dimensioning and tolerancing are going to be very objective. So there's hard and fast rules about what you can and can't do. Whereas some things will be more subjective. One person might do it this way, one person might do it another. It's all in understanding the rules and the guidelines in the ASME standard. Luckily, when people make drawings, they're typically on a design team, so you have engineering, draftspeople, all working together to put their best foot forward and get the best thing on paper. So you have multiple opinions, and usually the right product comes out. Dimensioning mechanics are the instructions and guidelines for what size and spacing to use for all of the components of a dimension. So there's a couple components in typical dimensioning. We have our extension line, dimension line, and our leader line. So we've already talked about things like line weights, how thick the lines should be, more or less what they should look like. Now we're going to talk about how they get used. Dimension lines are always parallel to the distance dimensioned, with an arrowhead on each end of the dimension line. They're going to be broken in the middle for the dimension value. So they're going to look something like this. We have a square box. This is our dimension line. So what it's dimensioning is the distance between this and this. If you noticed, it's parallel to the thing it's dimensioning. It's got two arrows. It's broken in the middle for the dimension. The next thing we'll talk about is the extension lines. These are going to be all over the place. What extension lines allow you to do is indicate where that dimension line applies. If you didn't have extension lines, you would have to put the dimensions inside of the part. The inside of the part would get very, very crowded very quickly. So extension lines allow you to put that on the outside of the part. Extension lines extend from the part being dimensioned. There's going to be about an 1/8 inch overhang from the dimension line. So this will be about an 1/8 inch here and here. Doesn't have to be perfect. It really just has to look right. But an 1/8 inch is a good starting place. And then the edge of the part, I'm going to draw that to be a nice square edge. There's going to be about a 1/16 gap. You never want the extension lines to touch the part. It makes the drawing hard to read. You start getting all these extension lines all over the place. Even though they're different line weights, if they connect, it'll kind of look like the part extends outward, depending on how it was drawn. So this little gap will be about a 1/16 of an inch. Center lines can be used as extension lines when it's applicable. So say we had a symmetric part with a hole in it, and we had a center line going through the part. We could dimension, we could put an extension line right here, and we could have that dimension line go to that center line. So it's indicating that the center of this is this far away. It's not as common, but it can be done. Arrowheads, which we've already seen a few right here, are typically an 1/8 inch long, although different CAD programs will have slightly different dimensions for them. They're typically filled in, that whole part right there, typically not open, and they're going to touch the extension line. So this is going to physically contact here. Let me draw it better here. They're always going to, leader lines are used for local notes that point to a specific feature or area. They must line up with the center of a hole, and they have a little bent area toward the top, which I'll show you in just a second. So I have a few examples of leader lines going on here. And the first one, this is a hole call out, which is a very common use of a leader. If I followed this line and drew an invisible line, it would go through the middle of the circle. The other way to do it would be something like this. Where it does not contact the middle of the hole. This is wrong, this is right. If a note uses an arrowhead pointing toward an edge, it means that the face of this that you can't see because it's in projection will have this applied to it. So if we did this in orthographic projection, we show the right side of this part. Right, so we took this part, now we're looking at it this way. We see the hidden lines of the hole going through it. This face would be chrome plated. If we have a filled dot on the end of our leader line, it applies to the surface parallel to the view. So in this case, this surface will get paint, or this surface on this view, because they're the same thing, okay? It's two uses of a leader line. They're popular for local notes, which we'll talk about in the future, but a local note just points to a specific area, doesn't apply to the whole drawing. Another item with the leader line is this little shoulder here. This is typically 1/4 of an inch long, and it's bent so that this can be read from the bottom of the drawing. So if you notice all the text, you can read it from the drawing without turning the drawing around. We've got a lot of symbols to deal with. You need to memorize these. They're going to be on every drawing. And because we have the ASME standard to reference when we're interpreting drawings, there will not be a legend to let you know what these are. Symbols are highly recommended and most of the time mandatory from ASME. They make the drawing more clear to everybody, and they save space. Older drawings would spell out or even abbreviate things like diameter or counterbore or countersink. Abbreviations are allowed but frowned upon because different people have different ideas of what an abbreviation might possibly mean. The symbols only have one meaning, or in some cases, two meanings, depending on how they are used. So the symbols we're going to deal with are diameter, radius, spherical radius, controlled radius, places or by, which is the X symbol, reference, which is the parentheses symbol, arc length, slope, square, which just indicates that something is a square, so you only need one dimension, counterbore, spot face, countersink, and depth. We're going to talk later about how to use all of these, but it's just enough for now to know what they are and what they mean. Let's talk about some of the dimensioning schemes available. There's two major ones in use: unidirectional dimensioning and aligned dimensioning. In this class, we're going to use unidirectional. Unidirectional dimensions read from the bottom of the drawing. So just like we talked about, the drawings are level with the bottom, okay? This is unidirectional. It's a little easier to read compared to aligned dimensions. Aligned dimensions read from the bottom or the right of the drawing. So aligned dimensions would look like this. So when you have the drawing, in order to read, you gotta move the thing around to get a good sight line on all the dimensions. These are common in architectural drawings and construction, boat building, that kind of thing, but they're not really used on engineering drawings. The global rule of making drawings is to make it clear and not confusing to the reader, while staying within the rules and guidelines that we'll talk about. Some of the important rules are that extension lines can cross each other, although you don't want anything to cross anything else if you can avoid it. Dimension lines should never cross other dimension lines or leader lines. So a quick example of that. I want to avoid this, where a leader line crosses a dimension line, right? The way I would do it, I just move this down here so it doesn't have to cross anything. It's more clear to read this than to deal with this kind of jumble going on. There's a couple different ways to show small dimensions. Occasionally you don't have room to put a dimension line with the dimension inside of it between two extension lines. So on occasion, you have something very small, you're dimensioning, you can do things like this, and I'll provide a picture to show you a couple ways to do it. A couple other things with dimensioning. We want to do something called dimensioning in between views, which just means if I wanted to dimension the width of this feature, instead of putting it up here, which is sort of okay, but not really, I want to put it right here, right? The reason, if I put it right here, I can look up and see where it's supposed to be right here, right? So with one glance, I get a better feel for what's going on in the drawing without my eyes darting all over the place. Another rule is to never dimension to hidden lines, right? So if I have this hole right here, I can see it because I have the hidden lines. I know it's there. But I don't want to dimension to this. I don't want to dimension its location to the center line, so I wouldn't want to do that, and I wouldn't want to dimension the size of the hole on this view. It'd be preferable to do it up here, because now I can clearly see the shape of the hole and I can see where it is, right? That's just one of those things that takes practice, but when you see drawings done incorrectly, you'll be able to pick it out. Another big thing is something called contour dimensioning, which we've already talked about a little, even if we didn't really know it. You want to apply dimensions to the most descriptive view for that given feature. So if we're talking about this hole, the most descriptive view for this hole is this view. It clearly shows us the shape and clearly shows us where it is in relation to other things. If we wanted to show the width of this, it's the most clear in this view, not this one, right? Because in this one, we only get the one bit of information. The same, if we wanted to show the height of this part, it would do it in this view, not this view, right? Because we can't get a clear view of it over there. So next is the cylinder rule. In older drawings, it was commonplace to dimension a thing like this all in this view. So you'd put all the diameters over here, which I can do, right? So that's diameter something. This is diameter something, and this is diameter something, right? And then I can just dimension, the height of all the cylinders on this view, right? It's more clear to dimension diameters on what's called the rectangular view. So if I dimension this on this view, it's more clear than on this view, right? The same with this one. I would like to dimension it on this view. I'm going to run out of space really fast. So showing it on the rectangular view is a little more clear. One trick you'll see a lot, I don't think they mention it in the book. I can't take this diameter off of this view without making this view superfluous, right? I'd have to take it away if I had no information. So you'll see a lot with parts like this is the largest diameter will be on this view, everything else will be on the other view. It's just kind of an excuse for the draftsperson to keep this view in there just in case they need it for something else or to add a little context to the part itself. Let's talk real quick about over-dimensioning, or more commonly called double dimensioning. There should only be one interpretation to the dimensions on a drawing. That means that each feature should only have one size and one location. You can get into hot water when you have a lot of different dimensions going on, because what will happen, you'll have the overall length of this part is this plus this plus this, right? So if this is plus or minus half an inch, this is plus or minus half an inch, plus or minus half an inch, the overall length can be whatever the dimension is, plus or minus half an inch. That's already figured, right? You already have all the information you need with these three dimensions to know the overall length of this part. If somebody comes over and adds another dimension, now you have two interpretations for what this part is. You could say the overall length is whatever this is, or you could say the overall length is this plus this plus this, right? That's an example of double dimensioning. It should never be on a drawing. It just leads to problems. It's incorrect drafting practice. One way we get around double dimensioning, say you're sending this off, you just want whoever to know approximately how long it is without having to add things together. Not a big deal for this part. I got 3 dimensions, but what if it had 20, 30, 40 dimensions, right? What you can do is add something called a reference dimension. So this is where our symbols come in. All I do is put that in parentheses, and that indicates to the reader of the drawing that that's now a reference dimension. What a reference dimension means is it's just for information. You can't use that to justify manufacturing or inspection. You don't inspect that number. It's just to reduce shop arithmetic, but you don't want to design your fixtures or anything around it. It's just for convenience. There's not going to be a ton of them on drawings. They're somewhat discouraged. They should really only be on there when they're absolutely needed to save time. Let's chat about some ways of dimensioning chamfers. Chamfer is just a beveled edge on a surface used to knock off a sharp edge or to allow relative motion. How it normally works is if one object is inside of another, say a slide or something, the bigger object with a groove through it will have a fillet, right? That's how machines make things. The end of your end mill will have a little round thing that'll produce a fillet. The object going inside of that will need a chamfer to clear that fillet. So it'll end up looking, there we go. So right here, you have an object with another object sliding in it. This middle one will have a fillet because that's whatever your machine tools make without having to go through extraordinary effort, without having to EDM. But this part, because it can be flipped up in a machine normally, can have a chamfer added to it very easily. So this chamfer just exists to clear that fillet to allow the relative motion. Just an example, there's lots of things fillets are for, but that's one of the design considerations. So there's about 3 ways to do a fillet, to dimension it. We've got linear by linear, right? So this just gives us a number by a number, right? So from here to here, it's be 20 thou, from here to here, 20 thou, easy, right? The next is linear by an angle. So we got 20 thou by 30 degrees. We don't have tolerances on these because it's just an explanation, but it's worth knowing that this 30 degrees will have a tolerance. It'll either be on the drawing or in the title block. The next way is to do a note, right? So the note can be linear by linear, or the note could even be, linear by degrees. This is an example of a symbol. This is the by use of the X. So it's saying this by this. The other use of the X symbol is when you have more than one of something. So say we have a plate, 1, 2, 3, make it 4. 4 holes. So in this instance, the X means 4 of this size hole. The location of the holes has to be done separately, but this one dimension controls the size of all 4 of those holes. The difference in usage, there's going to be a space before and after the X on the by. With this one, there's no space between the 4 and the X, but there is a space right after it. So just little things to watch out for, but this is all in the ASME standard. The next thing we're going to talk about is the difference between chain dimensioning and baseline dimensioning. Chain dimensioning is when all the dimensions are end to end, so they stack. So we've got this feature, and then this feature. If we wanted to know the length of this part, we have to add this, this, and this. Simple, right? The tricky part, and a phrase to remember, is that tolerances always add. So if this is plus or minus ½ an inch, this is plus or minus ½ an inch, plus or minus ½ an inch. This can vary by 1.5 inches at the max and minimum. Chain dimensioning has the most variation in overall length, but it's the easiest to produce. You have the most freedom. Baseline dimensioning takes all its dimensions from one place. So if we look at the overall length of this part compared to this part, it's going to be whatever this is plus or minus whatever this is. So say this dimension is plus or minus ½ an inch. This part can only vary plus or minus ½ an inch in total length. But, and we'll get to this when we start talking about GD&T, all the measurements and the inspections and how you make it needs to come from here. This would be our baseline, and this is where the idea of datums will come from. A few other topics to cover: the difference between location and size dimensions. Location dimensions indicate the location of a feature relative to other features. So where is the hole on the part in the X and the Y axes, or with an angular relationship like a bowl hole pattern. Size dimensions indicate how large or small something is. So what's the diameter of the hole? What's the radius of the fillet? Reference dimensions are for information only. They're not used for inspection or manufacturing. They're just to save time in reading a drawing. Tabular dimensions are kind of a space saver. They're going to use letters instead of dimensions to show what a part should be. So where you see these a lot, say you have a cap screw. So you got whatever the diameter of the cap screw is and whatever the length of the screw is. You'll have a table somewhere. You'll have a table that indicates what those values are for different parts. That way you only have to make one drawing for something that doesn't really change that much, like a screw. If you ever go to McMaster Car and look up, screws, bolts, washers, that kind of thing, this is generally how they're dimensioned. The other kind of dimensioning scheme is the coordinate dimensioning without dimension line. So this is a time saver with any kind of CNC machining. Say we have a square block with some holes in it. Instead of going through and dimensioning the location of every single hole, what we'll do, set up a coordinate system, right? So we've got our x-axis, our y-axis. We know where 0 is. We can label all of our holes, and then we can come down and we can indicate where hole A is with X and Y. So maybe hole A is 2 inches over in X and 4 inches in Y. So 2, 4. Hole B might be 3 inches over in X and 1 inch in Y. So when you're punching this into a computer, it can save you some time, because this is how computers think, in X's and Y's. The most important part with this is establishing your Cartesian coordinate system, which is just the X and the Y. Typically, they're only done in 2 dimensions, so left, right, up, down. The last thing we'll talk about in this lecture are notes. There's 2 kinds of notes: local notes and general notes. General notes are usually in the top left of the drawing, and they say things that apply to the entire drawing. So it might say something like surface finish, 63 microinches or better, unless otherwise specified. Unless otherwise specified is often abbreviated to UOS. It's extremely common on drawings. It's a draftsperson way to cover up, right? So say they forget to put 63 microinches on something on the drawing, they're covered by that general note that applies to everything. So I could say something like, paint everything red unless otherwise specified. It lets the drafter go back in and they could indicate a spot, don't paint, with a local note. A local note points to a specific area or a feature and has some instructions for what to do with it. So chrome plate here, paint here, or surface finish, whatever it needs to be in an individual spot, but it does not